Okay, so we're on page 477 of your workbook. So if you can turn there now, 477, we're going to pick up, we're going to talk about functional notation in relation to problem solving. So kind of bringing all the elements we've learned this unit together. So this is our last lesson, and tomorrow would be a review. The next day would be your unit exam. So we talked about functional notation. So if you have a word problem, often the equation is not going to be y equals something, right? Y and x. If you have a word problem like 2x plus 3, so that would be the equation for a general function. But what if you have a word problem and your equation is something like h equals negative 2t plus 12 in terms of the height of the candle over t in t hours. Okay, so if I wanted to write that instead of an equation, what if I wanted to write that as functional notation? Well, in that case, it wouldn't make sense to use y equals because we want to use the variables h and t. And so our y variable, or our dependent variable, our output, would be h, our height, and our input is time. So we would instead write it as h of t. We'd write it as h of t instead of f of x because in this word problem, height is a function of time. We input the time and output is the height of the candle. So depending on how long we're running or lighting the candle for will affect how the height of the candle. Okay, so we would use those variables instead of using f of x. We would use the variables, so h of t, because height is a function of time. So looking at this problem here, let's grab our graphing calculators, and we're going to graph this function h of t. So it's still like y equals, right, when we plug it in our calculator, because your calculator only works with those two variables, so we'll just make it. So we'll grab our calculators, go to y equals. Come on, calculator. Why are you being like this? Try again. Nope, let's try opening it one more time. Okay, so let's go to y equals. There we go. And type in negative 2x plus 12. Make sure you're using the negative symbol and not the minus symbol. Okay, so don't think, yeah, okay, so we got that in. Let's see if we can see, let's push graph. Now remember, right now we're in standard windows. And to be in standard windows, you'd push zoom 6. We want to be able to see the x and the y intercept, so I need to go a little higher. So my windows, I'm just going to change my y max to 20, so that I'm going just a little bit higher, so I can already see the x intercept, but I want to see the y intercept. So there it is. Okay, so there's our window. So I used negative 10 to 10 still for x, but for y, we did negative 10 to 20. And we could have changed that because we don't need negative values, right? If we're dealing with height as a function of time, and so this is the t variable, this is the h of t variable on the y, we don't need the negative, right? It doesn't make sense to have negative time or negative height. So our graph looks something like this. Okay, not knowing what our intercepts are just yet. It says determine the value of h of 5. So h of 5 would be at 5 hours because our input, our time, is 5. The input is 5. Right? It's inside the brackets. That's your input. So negative 10 plus 12 equals 2 centimeters because our height is in centimeters. So after 5 hours, we are at a height of 2 centimeters. So after 5 hours, the candle is 2 centimeters high. Okay, has a height of 2 centimeters, I guess would make more sense. So the next one is, it says evaluate the following and explain each of their significance. So h of 0, So now my input is 0, or time is 0. So at time of 0, remember if you want to use your calculator, you could go trace 0, enter, is 12. That's equal to 12. So what that means is, in the beginning, the candle is 12 centimeters. So at time 0, so at the very beginning, our height is 12 centimeters. So that would be the initial height of the candle before it starts to burn. H of 6, so again, let's use our calculator. Trace 6, enter, gives me 0. Oh, look at that. So this is 6, and this was 12. We can add that on our graph. So that means after 6 hours, there is no more candle left. The candle has burned to the ground, has burned down to 0. Okay? And H of 8, so let's go trace 8, enter. Well, that gives you -4. So does that actually make sense? So if that is -4, in terms of this function, it has no meaning. Because after 6, the function doesn't exist anymore. So that has no meaning in terms of this equation or this function that we're dealing with because of the context. It says, how long will it take for the candle to burn down to a height of 7? So now we know our output, right? Our height is 7, or our y value is 7. So remember, how do we do this? We go to y equals, well, there's two ways. I'll show you algebraically or graphing calculator. So graphing calculator, I put y2 as 7. I push graph, and we're looking for the intersection point. So how do I do that? Second, trace, see intersect is number 5, and push enter 3 times. 1, 2, 3. And that gives me 2.5. 2.5 hours. Okay, our time is, or x value is 2.5. You could have also used your equation, so you could have gone 7 is equal to -2t plus 12. So if I subtract 12 to both sides, I get -5 equals -2t, and then divide both sides. Let's extend this. Divide both sides by -2, and that gives you 2.5 is your time. Okay, 2.5 hours. So it'll take 2.5 hours. I suggest an appropriate domain and range. So the best domain and range for this graph is because where the function actually exists. In terms of this function, the domain would be, well, let's see, time. Now we're going to use, instead of x, we have to use the t variable. Time is between what two values? So how far left does the function go? It exists between time of 0 hours and 6 hours till when it's completely burned out. The range, how high does it go and how low does it go? So the lowest height it'll be, so we're going to use h instead of y, that's important, is 0. So it's going to get to 0, and the maximum height was what it was at the beginning, which is 12. So that would be your domain, and that would be your range. So when you have these contextualized problems, you really have to figure out your domain and range based on the context of the problem. You can't just use the equation and what you see on the graphing calculator. Because if I just looked at this blue line on my calculator, that equation looks like it's XER and YER for our domain and range. But in terms of the context, it's not. So when you have these contextualized problems, you have to determine what that domain and range is based on the context. And usually, it's going to be a context where you can't have a negatives. So that's often the case. Okay, so that's, if you can, that was the example from lesson 10. The assignment from 10 is numbers 1 to 3 and number 5. Let's turn in your books now to lesson 11. So lesson 11 is on page, let's see here. It's a short lesson today. 481. So turn to 481. So it's really important that we can interpret, and this is kind of, related to Science 10. So if you've done physics and Science 10, which we're kind of the end of the year of grade 10, most of you probably have, which is good. It's going to help you. So we're going to talk about some of those concepts today a little bit. All right, so let's look at this one. It says the Carter family are driving to Yukon for a family vacation. The graph represents the amount of fuel. So that would be my dependent, our dependent variable. In the gas of the tank of their car on the first day of their journey. So time is the independent. Okay. So notice how they have these little letters there, and they're dividing it into 8 line segments. So with reference to the journey, explain what's happening between A and B. Okay, so from A to B, it starts with 50 liters in their tank. And what are they doing? Probably between 7, this would be 8, 9, 10, how many hours would that be? Between 7 and 10. So for 3 hours, they're driving, right? They're driving at a constant rate, because it's a straight line, for 3 hours, because they're burning fuel at a constant rate. So they're probably driving at a constant rate, maybe cruise control. Okay, so B to C. So that looks like for 30 minutes, right? That would be about 30 minutes from 10 to 10:30. So for 30 minutes, they're stopped. The fuel is not changing. So they're stopped, or they took a break for 30 minutes. And then from C to D, all of a sudden, the fuel in the tank at C to D goes from 20 liters to 60. So that looks like they fill up their tank. So they're refueling their tank. So obviously a full tank is about 60 liters in their vehicle. Okay, what is the rate of fuel consumption? It says in liters per hour between D and E. So between D and E, if we want the rate of fuel consumption, we need to figure out how much fuel did they lose and how long did it take them to lose it. So how much fuel was used between D and E? Let's look at this. We started at 60 and we're finishing at, E is at, I think 25. If you have a ruler, it'd probably be more helpful. So 60 minus 25, what does that give us? Fuel used would be 60 minus 25. 35 liters is what they used. And how long? Because we want liters per hour. So for how much time did it take them to burn 35 liters? So let's see, they started at 10:30 and we went to here, which is 1 o'clock. They're using 24 hours. I'm going to use 1 p.m., 2 p.m. Or I guess we can do 24 hours. So 1,300 hours, 1,400 hours. So how many hours is that? It would be 1, 2, 3.5, right? 1, 2, 3.5 hours. So our fuel consumption would be a rate, so we're going to divide them. 35 liters, because we want liters per hour, divided by 3.5 hours. And so when you divide that, we get 10. 10 liters per hour is the rate at which they're burning fuel. Okay, so which line segment represents the car being refueled for the second time? So that would be here, GH. GH. And last question, calculate the total, or I guess there's 2 more, the total time when the car is being actually driven. So be careful, we're not including brakes. So the total time the car is being driven. So there's 2 ways you can do this. You could take the whole trip and then subtract off the time that you're not driving, right? So we start at 7 o'clock and we finish at 1700. So that would be 10 hours. How long were they braking for? So here was 30 minutes. And then they also did a 1 hour break, right? So if they're on the road for 10 hours, like in their car, minus the 1.5-hour breaks, they're actually driving for 8.5 hours. So they're driving for 8.5 hours. Okay. They said if fuel costs 85 cents per liter, calculate the cost of the fuel used for the day of the journey. So what we need to know is the total amount of fuel being burned. So let's do all the line segments where they're driving. So they're driving A to B. They're driving DE, FG, and HI. Okay, so A to B they're driving. We're driving A to B. We're driving D to E, F to H, and H to I. So we need to know how many liters they used in each time. So from A to B, they went from 50 to 20. So how much liters did they use? 50 minus 20, or 30 liters. Okay, D to E, I think we found D to E already, right? It was 35 in question B, 35 liters. Plus FG. So FG, they were at, oh man, a ruler would be really helpful, 25, and they finished at 15, I think that is. So that would be, how many liters did they use? 25 minus 15, or 10. So 25 minus 15, or 10 liters. And then HI, they went from 60 to 50. So 60 minus 50 is another 10 liters. Okay, so our total liters used for driving that day would be, so 30 plus 35 is 65, plus 10, 75, plus another 10 is 85 liters. And so if the cost is 85 cents, so 85 liters times 85 cents per liter gives us times, 85 cents per liter, $72.25. That was per liter. Okay? So that would be your cost. All right, so let's look at just the other next page, and then we're done for this lesson. So we're going to look at example 2 and 3. So it says, suggest a possible scenario for each of the following graphs. So when you have something like this, you might want to break it up into its line segments. So here, this is a graph. It's not distance versus time, it's speed versus time. So be very careful with that. So we're going to break it up into the different line segments. So 1, 2, 3, 4, 4, 5, and 6. I'll zoom in a bit. Okay. So we're going to break it up. So what's going on, we can keep it simple. We don't have to go into like a huge story, but what's happening with the speed over the time there? Car is traveling at a constant speed, right? They're maintaining the speed. I don't know what the speed is, but they're maintaining that speed. It's a constant speed. So in 2, they would be slows down. So those maybe slows down for construction. I don't know. Then he's traveling at a slower constant rate or constant speed. And what's going on in 4? So all of a sudden, he increases his speed. 5 will be what? He's going at a steady, constant speed, but still slower than earlier, so slower than 1. And then 6 would be he slows to a stop. Okay, so you got to be able to interpret that. So if this was a distance time graph, it'd be very different. There's a speed time graph. Okay, I could take the same problem, make it a distance, same graph, and I could have made it a distance time graph. Okay, so if I made this a distance time graph just